Another example of a static equilibrium problem is something like this. Two ropes supporting a ruler with mass 18 grams. The ruler is 30 centimeters long. The ropes are at x equals 1 centimeter and x equals 27 centimeters. Mass of 75 grams is placed at x equals 12 centimeters. Find the tension in each rope. And this is actually, we're going to do a mini lab that will basically be this exact situation. So what's going on here is we've got a rope, we've got a ruler, we've got our rope anchored at the other end of the ruler, and then we've got a mass chilling out somewhere on the ruler. So this is 1 centimeter. Over here we're at 30 centimeters. No, sorry, 27 centimeters. Up to here, the whole thing's 30 centimeters long. And then this mass is at 12 centimeters. All right, so what we have two tension forces, T1, T2. We've got gravitational force on the ruler, and then we've got gravitational force on this mass, whatever that might be. And our first step is to pick a pivot point. Easiest thing to do, put it at where one of the ropes is attached. It doesn't matter which one, I'll just choose the left one. And then start writing our equations. Our torque equation, it's hanging there. We know some of our torques is 0. This is 1 centimeter in, so this mass at 12 centimeters. Well, first off, it had a mass of 75 grams, 0.075, 9.8. It's at x equals 12 centimeters, but our pivot's at x equals 1 centimeter, so that's 11 centimeters away. And that's a force downward, which would cause a clockwise rotation, so that's a negative torque. Also a negative torque is the weight of the ruler, which would be 0.018, 9.8, and we'll assume that the ruler is uniformly distributed. So the center of mass is at x equals 15 centimeters, pivot's at 1, so that's 0.14 is our R. And then we have a counterclockwise positive torque from T2, which, being at x equals 27, is 26 centimeters away. We can use that equation to calculate T2. In the y direction, sum of the forces is 0, and that's, again, straightforward. We have T1 plus T2 minus the ruler's weight minus the mass's weight. And that'll enable us to calculate what these values should be. If we punch that into our calculator, 0.075 times 9.8 times 0.11 plus 0.018 times 9.8 times 0.14 divided by 0.26 gives us that T2 is 0.4059, etc. And then if we plug that in down here, 0.4059 minus 0.018 times 9.8 minus 0.075 times 9.8, which is what would be on this side of the equation, then we move that over to the other side, it becomes positive. So the tension in the first rope is 0.505, etc. newtons. And this is basically exactly what you're going to do. Oops, I got it off here. This is exactly what you're going to do in the lab, except instead of these two ropes, we're going to have what are called spring scales. So you'll be able to measure how much force they're exerting, and you're going to compare that value to the value that you calculate. We can also do problems that involve forces in both directions. Now this is a long problem statement, but bear with me. We've got a hanging sign with mass 2.4 kilograms that's uniformly distributed over 78 centimeter length. One end of the sign is bolted to a wall, while the other end is attached to the wall by a cable. It's angled at 35 degrees above the horizontal. Find the tension in the cable, the horizontal and vertical components of the force exerted by the wall on the sign. So we have one end, we've got a sign, and one end is attached to the wall. So here's our sign, and the sign is uniformly distributed mass, so its center of mass is right in the middle of its length, which is 78 centimeters. And then this far end is attached to the same wall by a cable. That makes an angle of 35 degrees above the horizontal. Alright, and this is a case where we can use our forces and torques to solve. One thing that's important to know, if this is attached to the wall here, there's going to be an upward force exerted by the wall that's holding up the sign, and there's also going to be a horizontal force that's balancing out the horizontal component of this tension. Right? So, sum of our torques is 0. You got to think about where a good spot is to put our pivot. Well, I would put it right here at the wall because there are two forces that we can totally eliminate from the torque equation that way. So, time to draw this picture a little bit bigger. So we can say that the sum of our torques is 0, and we only have a couple of torques acting. First off, we have a torque from the weight of our sign, got a gravitational force on the sign, and that is equal to mass times gravity, and it's uniformly distributed, so that's acting 39 centimeters from the wall, and it's going clockwise. That is a negative torque. We also have a torque from the tension going in the counterclockwise direction. Force is T. And remember, we've been doing, torque, remember, is F sine theta times R. We've been doing a lot of just FR because our forces in our lever arms have been perpendicular. Now they're not perpendicular, so this is just T sine 35 times distance from the pivot, which is 0.78. So that's our torque equation. We're going to use that to find tension. And in the x direction, we only have this x component of force from the wall and a component of tension, which would be the cosine 35, and that's going to be equal to 0. In the y direction, sum of our forces is 0. We have an upward component of the tension. We have this force in the y direction, and then we have the gravitational force acting on the sign. Oops, 2.4. So then we have three equations, and we can solve for our three unknowns that we wanted to find. When we move this over, it becomes positive. 2.4 is 9.8 times 0.39 divided by 0.78 sine 35 gives us that our tension is 20.5-ish newtons. And then we can plug it, I'll store that as T, because I'm going to need to use it twice. And plug it into here. We just get the x component of the force exerted by the wall is just T cosine 35, which I can punch in to get that. It is 16.795, whatever, newtons. And down here in the y direction, the force in the y direction would be, we move this over, it becomes positive, 2.4 times 9.8, and this becomes negative, minus T sine 35. And we get that the y component of the force is 11.76 newtons. So that's an equation we can solve using both x and y directions and torque. Another problem that you might see that I want to talk about, but I'm not going to do a calculation with numbers, is that if you have a ladder resting against a wall, so this is the ground, this is the wall, and then you've got your ladder leaning at an angle, some angle that you'll be given, and the ladder has some length L. In this case, we would have a normal force from the ground that's going up, and we also have friction from the ground, static friction. Over here, we would have a normal force going outward from the wall, and then we'd also have static friction holding the ladder up. So this would make for some a fairly complicated torque equation. Let's look at our forces first. In the x direction, all we have are, oh, and we also have the gravitational force acting on the ladder, of course. In the x direction, we have the normal from the wall, and we have the friction from the ground. In the y direction, we have the normal from the ground. Oh, this is 0. We've got the normal from the ground going up, we have friction from the wall going up, and then we have mg going down. And the torque equation is pretty complicated. I would set my pivot down here, or up there, because it eliminates two forces. And then we have to think about some similar triangles here. We have a torque from mg. Then the question is what the angle is. Well, this is theta, which means that this is 90 minus theta. So mg sine of 90 minus theta, which becomes cosine of theta, times r, and the distance this is from that pivot point is half the length of the ladder, L over 2. By alternate interior, this angle is the same as this angle. So then we have, oh, and this is a clockwise torque, so that would be negative. From the wall, we have a counterclockwise torque, so that would be positive, normal wall. This angle is the same as that angle, so that's a sine theta times L, because it's the full length of the ladder away. And then for this one, if we extend this out, this is the same angle, theta, so this would be 90 minus theta, so, and that is, again, a counterclockwise torque, so we have a plus friction from the wall, cosine theta, L. And so that's how you'd go about setting up the ladder problem. And I'll probably give you one of those on a test or a quiz at some point. So be prepared to deal with that. For all of these static equilibrium types of problems, I don't want you to memorize how to solve a particular situation. I want you to understand the principles of writing the force and torque equations so that you can solve a problem, even if it's a totally new problem I've shown you before. And I really don't want you to memorize, this is the equation for the ladder, this is the equation for the sine, this is the equation for the diving board, because they're all coming out of the same principles, and I want you to understand those concepts rather than just trying to memorize a whole bunch of different situations.